In this lecture, I'm going to be talking about the 9-point circle theorem and its proof. So we start with an arbitrary triangle, and we look at each of the edges and look at the midpoints of those edges. And then we take the altitudes and look at the feet of the altitudes. So the feet of the altitudes is where the altitude hits the base. You will remember that we showed that the altitudes all intersect at a common point, this point here. So we want to go from this point to each of the vertices and take the midpoint from this point to each of those vertices. So this will be one of the points going from this intersection point of the altitudes to this vertex up here. We do that for each of the vertices. And the 9-point circle theorem tells us that no matter what the triangle looks like that we started with, these 9 points are all going to lie on a circle. So again, the points are the midpoints of the sides, the feet of the altitudes, and then going from the intersection of the altitudes to the vertices, we take the midpoints of those. We get these 3 points, and all 9 of those points will be on the same circle. Here is the statement of the 9-point circle theorem. So we have the 3 vertices of a triangle, A, B, and C, and we let M sub A be the midpoint of the edge opposite A, so it's midpoint of BC. M sub B is the midpoint of AC. M sub C is the midpoint of AB. And then we look at the altitudes. The altitude from A hits the other side at P sub A, so P sub A is the foot of the altitude. And then P sub B is a foot of an altitude drawn from B. And P sub C is the foot of the altitude drawn from C. We let D be the intersection of the 3 altitudes, and then we're going to look at the segments going from D to each of the vertices. So we look at A sub D, AD here, this segment, and we want to take the midpoint of that segment, and we're going to call that Q sub A. The midpoint of segment BD will be Q sub B. The midpoint of segment CD will be Q sub C. Then we have our 9 points, the midpoints MA, MB, and MC, the feet of the altitudes P sub A, P sub B, and P sub C, and then the points Q sub A, Q sub B, and Q sub C, and all 9 of those points will be on the same circle. In addition, we're going to show that the center of this circle is the average of the vertices and the intersection of the altitudes. So A plus B plus C plus D divided by 4. So let me show you all the points in this picture. So the M's, again, are the midpoints of the sides. The P's are the feet of the altitudes. The Q's were the midpoints of the segments going from D to each of the vertices, where D is the intersection of the altitudes. Let me also put in the point N here. N is going to be the where we want to prove the center of the circle is. That requires a proof, but n will be then the average of the 4 points A, B, C, and D. To prove the 9-point circle theorem, we then just need to show that the distance from this point N, so it looks like this D here, don't mistake that for this point. D is this point here, the intersection of the altitudes. This is N. And we want to show that the distance from N to each of the 9 points we're interested in is the same. And that then will show that the 9 points are on a circle and that the center of that circle is N. To do this, we're going to use a lemma. And let me describe this lemma with a different picture here and then give the proof. So the picture for this lemma is that we have 3 points A, B, and P. The midpoint of the segment AB is O. O is the average of A and B, the midpoint of AB. And we're given that the P point satisfies angle APB is a 90-degree angle. What we want to prove is that OP, that distance, is the same as OB or OA. All three of those distances are the same. These distances are clearly the same because O is the midpoint of AB, but we want to show that OP is also equal to OA. So notice that's the same thing as saying that P is on the circle centered at O of radius OA, because then that will make OP and OA the same. So that's what we're trying to show, that in the situation that we had with the angle here being a 90-degree angle and O the midpoint of AB, that P has to be on this circle with diameter AB. You may recall that the opposite is true, that if you have a semicircle and you take a point P on the semicircle, that if we go from the endpoints of this diameter to P, and we look at this angle here, that it's going to be 90 degrees. The purpose of the lemma is just to make sure you're aware that the converse of that is true, that if this angle is 90 degrees, P has to be on the circle. It could be on the other side of the circle. If I drew my circle this way, it's possible P would be over here, but P has to be on the circle with diameter AB. And we're actually going to prove both of these, the if and only if, that the angle here is 90 degrees if and only if P is on this circle with diameter AB. But we're mainly interested in the direction of the lemma. So let me look at this and think to myself, what I want to show is that O minus P squared equals O minus A squared. Remember, we use this for distance. This is the distance from the vector PO. It's a distance squared. So distance squared of that vector. And this is distance squared of the vector from A to O. And we want to show those are the same. And that's the same thing then as saying that OP equals OA. That those distances are the same. So what I want to do to show you this first is to replace the O here with what it's equal to, the A plus B over 2. So again, O was the average of A and B, and I just did a simple substitution there. So we would like to know if this is true. What I'm going to do to tackle that now is to use the following, that x squared equals y squared if and only if x plus y times x minus y equals 0. And you can see here, if I multiply this out, I get an x squared and a minus y squared. And the middle terms plus xy and minus xy cancel. So this looks like something fairly simple here, just a little algebra, but keep in mind this is not really what this is saying. These are vectors, and this is saying the length of the vector x equals the length of the vector y, or the length squareds, are equal if and only if you take the vector x plus y and the vector x minus y, and their dot product is 0, so that means these vectors are perpendicular. So that doesn't sound like algebra at all when I say it that way, but that is equivalent to what this is saying. The argument can be given, it's the same I just described, because the dot product satisfies the distribution law. So I can go ahead and distribute the products, and again, things will cancel, and we'll end up with x squared minus y squared for this, giving us the x squared equals y squared. And if you really want to convince yourself, because you don't believe everything I just said about vectors, go ahead and put AB here for this vector and CD here for this vector, and do the arithmetic, and you'll end up seeing that you get the same thing here for this equation as you do with this one, at least if you put everything on the same side. So to apply this identity, or this if and only if here, we're going to take this to be x, and we'll take this to be y. So we want to look at x plus y, this. We want to dot that with x minus y, this, and that should be 0. So what is the sum of these two? Notice this plus this is a plus b. We'll have a minus p and a minus a. Well, the a plus b minus a is just going to give us b. So when I add this and this together, the a is going to go away. I'm going to have a halves and minus a. And then I'll have b halves and b halves, which gives me a b and a minus p. So I'm just going to get b minus p for the sum. For the difference, this minus this, the a plus b over 2 cancels, and I'm just left with a minus p when I take this minus this. So we're going to get b minus p again when I take this plus this, and I'm going to get a minus p when I take this minus this. So we end up with b minus p times a minus p. The dot product of those two vectors is 0. Now, is that true? Well, this is the vector from P to B, and this is the vector from P to A. And you can see those vectors are, in fact, perpendicular because we're given that angle APB is 90 degrees. From the point of view of this lemma, then, we have that is true because we're given the information that the angle at P there is 90 degrees. So this dot product is 0. And now we got to think to ourselves, does that really justify that these two are equal, that these two distances are the same? Because we worked not in the direction we want to go in, we want to work in reverse that direction. And so we got to think to ourselves, can I work this backwards? Well, remember, if I call this x and this y like we did just a moment ago, this is x plus y and this is x minus y. That's where these came from. So if I think of this as being x and this as being y, this is just saying that x plus y times x minus y, the dot product, is 0. So because of the if and only if, that's going to mean x squared is equal to y squared. So these two are equal when I square them. And so I then can go ahead and say that this is true because this is just O. This is a definition of O. So I can work backwards, starting with this, getting this, and then getting this. Now it's easier to go in this direction, at least initially, because who would have thought to call this x and this y initially unless I had noticed that this was the same as this. But once we have this, we see this is true by the information given that this is 90 degrees, we can say this is true and then this is true. And so these two distances are the same. As I said, this is really proof going in both directions because if I start with these two distances being the same, that implies this, and then that implies then we have a 90-degree angle at P. So this goes both ways. P has to be on the circle if this is 90 degrees, and if P is on this circle, then this is 90 degrees. So now that we have that lemma, we can go forward with the proof of the 9-point circle theorem. And I'm going to do it in 3 different cases, and then we'll see how those cases piece together. The first case I want to consider is I want to show that n to q sub a and m sub a are the same, that those distances are the same. So in this picture, this is n again. Q sub a is here, m sub a is here. I want to show these two distances are the same. Now, if you look at the picture here, you might notice that maybe something stronger is true. Not only are they the same, but if I look at the line segment from MA to QA or QA to MA, this is just the midpoint. And in fact, that's how we're going to prove that these distances are the same. We're just going to show that N is the midpoint of the segment Q sub A to M sub A. And then that'll mean that N is right in the middle of that segment, and so these two distances will be the same. So all we do to check what the midpoint is here, we take the average of the two coordinates, Q sub A plus M sub A over 2, that average of those two vectors. This should be equal to, well, it's equal to 1/2. Q sub A is defined to be A plus D over 2. It's the midpoint of AD. That's where Q sub A came from. And so I just put A plus D over 2 for Q sub A. This 1/2 is coming from here. And for M sub A, that was the midpoint of BC. So that's just B plus C over 2. Now you just look at this. We have A plus B plus C plus D over 2 times 1/2. And so that's 1/4 A plus B plus C plus D. And that's the same thing as N. So in fact, N is the midpoint of QAMA, that segment. And that shows us that the distance from N to QA and the distance from N to MA are the same. Now, if I were to ask you to give me this proof, I could ask you to do something else instead, namely, I could change the letters around. We should be able to do not just N to QA and N to MA being the same, but N to QB and N to MB the same way. And you can see it still looks like N is the midpoint of MB QB. And in fact, the argument's the exact same. So I'm just going to go ahead and change everything here. I just change the letters around. I want to show here that N is the same distance to QB and MB. And again, I'm not going to go through this in detail, but you just do the exact same thing. You rewrite QB with B plus D over 2 because QB is the midpoint of BD. You rewrite MB as A plus C over 2 because MB was the midpoint of AC. And then that will be the same thing as this, which is N. And similarly for QC and MC. N to QC and N to MC will be the same. And you can see that in the picture here, MC and QC. The midpoint is N again. So we get that N is the midpoint for each of those segments. In fact, we will want to use the stronger fact that N is actually the midpoint of these segments. So not only are these distances the same, but N is the midpoint in this case of QCMC. There's one other comment I want to make before we move on to the next case. And that is namely that we have not shown that the distance from QA to N and QB to N and QC to N are the same. All we have shown is that the distance from N to QA and N to MA are the same, and the distance from N to QB and N to QB are the same, and the distance from M to MC and the distance from N to QC are the same. Now, they all look the same because they're on the circle, but we haven't proved they're on the circle yet, so we can't just look at the circle and say that. So as far as I know, it might be the case that the distance from QA to MA is different than the distance from QB to MB, and so these distances might not be the same. We still have something to prove there. But we do have what we have up here, this equality, whether or not the C's are A or B here, we have that equation being holding for case 1. Now I want to use the lemma. So this is for case 2. Case 2 is the following. I want to look at the distance from N and QA and N and PA and say they're the same. So in this picture, this is N again. We want to go to QA, which is here, and we want to go to PA, which is down here. And I want to say that these are the same. You can see it does not look like N is the midpoint anymore of QA PA, so we can't use that. but we want to somehow say these distances are the same. Notice that angle QA here to PA, that's part of the altitude, and the line down here, BC, are perpendicular. And so in particular, if I look at the angle going from A to P sub A to M sub A, that's 90 degrees. So we have a 90-degree angle there. So that's this angle. And if I look at this side, N was the midpoint again of MAQA. That's what we did in case 1. N is the midpoint of MAQA, and we have this angle is 90 degrees, and that's precisely what the lemma was saying, that this distance then has to be the same as this distance or this distance. So the distance from N to QA and the distance from N to PA is the same, and so we have what we want here, that those distances are the same. So again, since N is the midpoint of MAQA from the previous case, we get that from the lemma that these two distances, are the same. And again, that's also because this is a 90 degree angle. Okay. So that's case 2. And again, you can imagine I can replace the A here with B's or C's. And in fact, that's what we'll do. The argument's the exact same here, just to make sure here with the B's here. We're looking at wanting to show these distances are the same. We look at Q sub B, P sub B, M sub B. So Q sub B is here, and we go to P sub B, it's here, and M sub B. This is a 90-degree angle again because this was an altitude. So we have a 90-degree angle there, and N was the midpoint of this segment from MB to QB or QB to MB. And so, and this being 90 degrees, using the lemma, we get that this distance from N to P sub B has to be same as the distance from N to Q sub B. So we get this. And the same thing with C. So the distance from N and PC is the same as the distance from N to QC, and those C's can be A or B. It's the same case, really, same argument. So that's 2 cases. 1 case left. We need some room for this. I'll make it bigger when we need it. But I want to show that now N is the same distance from MA and MB. So here's N again. We're looking at M sub A and M sub B. And I want to show those 2 distances are the same. So let me start with that and see what we can use to show this. So really there's a question mark here. We don't know that this is true yet. Let's see what we need. So here we have x squared equals y squared, x plus y, and x minus y, that dot product being 0 are the same. And if I call this x then and this y, I can go ahead and use this if and only if, and use that x plus y dotted with x minus y is 0. So again, this is x and this is y. So that will say the same thing then as the sum of these 2, which is this. And the difference, well, this minus this, the end will go away, and I'll just have m sub a minus m sub b. And this dot product is 0. So this is true if and only if this is true. And now I want to go ahead and put down what m sub a and m sub b are in terms of this being a midpoint of BC, so it's B plus C over 2. And this being the midpoint of AC, this is A plus C over 2. It's a little long, so I've squeezed it in here. But again, M sub A is a midpoint of BC, M sub B is the midpoint of AC. And so I have that. N was A plus B plus C plus D over 4, but I have an extra 2 here, so I have 2N. So this becomes just 2 in the denominator here. And m sub a minus m sub b, again, b plus c over 2 minus a plus c over 2. And this will equal 0, and that's my version of a dot product. Okay, so we can simplify this. Notice we can take out a half from this expression, and we can take out a half from this expression. So that'll give me a fourth when I take out a half from both of these. So imagine the 2's not being here, then I'm just left with b plus c plus a plus c minus all these. And then b plus c plus a, well, when I subtract a plus b plus c, those are going to go away. I still have another c here and a d here. So I'm going to have c minus d. So I'm going to have 1/2 from here and a c minus d from there. And here I have the other half. And I'm going to have then b plus c minus a minus c. So the c's go away, and I just have b minus a. So again, this is coming from taking out a half from both of the parentheses above it, and then looking at what's left, we have b plus c over 2 and a plus c over 2, subtracting this. The a, b, and c go away. We're left with c minus d. That's this part. And again, the c over 2 will go away here. We're left with b minus a. That's this part. So we have that expression there. Let me put it there to make some room here. And let's just check where this is. Now I have the picture a little bigger. This is the vector from D to C. So from D to C here is this vector. So it's part of this altitude. And this is the vector from A to B. And so that's this vector from A to B. And that's just the edge, then AB here. And the altitude is perpendicular to it. So we do, in fact, have that the dot product is 0. This was an if and only if, this argument. So since this is 0, we will have that this has to be true. Again, this is 0 looking at the picture because this is part of the altitude to side AB. So we end up with this equation being true. The distance from n to m sub a is the same as distance from n to m sub b. And just to clarify, this is what I said the justification was on this last step, that AB is perpendicular to the altitude, so perpendicular to the line then going through C and D, and that's giving us that this last part is true. As before, we don't have to use A and B here. I could use A and C and do something similar. The argument would be almost the same. You should convince yourself of that. I don't have all the details down on the screen, but the argument's essentially the same. This is what we begin with, and if you go ahead and use that x squared equals y squared is the same as x plus y times x minus y equals 0, you'll get this in the end, and these are perpendicular. This is part of an altitude going to the edge AC, and so this dot product will be 0, and so we'll get that the distance from n to m sub a and the distance from n to m sub c are the same. For case 3, I only need those two equations, and we can wrap things up now. So let me just put that n there just to make room for other things here. We have all these equations we've shown. Now what I want to do is to look at these last two first, and notice this came from case 3, that the distance from n to m sub a is the same as distance from n to m sub b, and that's the same as the distance from n to m sub c. So all three of these are equal. I mean, if these two are equal and these two are equal, then these two are equal, because these are the same. So we have all three of these being equal. This is the distance from n to each of the midpoints. So we have that n to each of the midpoints, all those distances are the same. Then the next thing I want to do is to go up here and look at these three, which came from case 1. And let me go ahead and make room for the wording, in case you want to follow me with that. But we just comment that the distance from n to each of the midpoints is the same by looking at these two. Going up here, we know all these three are the same because we just said that. And so since these are equal to these, that means that all three of these have to be the same and the same as these. So the distance from n to the q's are all the same and equal to the distance from n to the m's. And then finally, we just said that all these are the same. And so since those are the same as the distance from n to the p's, then we have the distance from n to the p's are all the same as the distance from n to the q's are all the same as the distances from n to the m's. So we have all 9 of those distances being the same, the distance from n to each of the m's, the distance from n to each of the q's, and the distance from n to each of the p's. And so since we have that, that means the 9 points that we have here are all in a circle centered at n. So that gives us what we want. That proves the 9-point circle theorem and ends this lecture.